Assalamualaikum, salam sejahtera. So, ini sekali lagi yang di mana saya tak mengajar dalam video ni. Tapi saya just moderator je lah. Okay. So, dalam video ni akan diterangkan mengenai tangent vector. Okay, dan ada normal vector, binomial and curvature. Okay. So, what are the tangent vector? Dah kata dalam tangent vector dan juga normal vector.
This is the interactive figure, the unit tangent and principal unit normal vectors. In this figure, we have a curve that is traced from point A to point B. I can modify this curve by dragging the endpoints or dragging any of the blue control points that lie along the curve. On this curve also is a point P, and P remains on the curve as I drag it. Now, I imagine that this curve is the result of a vector-valued function that's dictated by a parameter, and as the parameter increases, point P moves from A to B. Now, there are two vectors sticking out of point P. There's the vector T that is tangent to the direction of motion, and the vector N that is perpendicular to T. How are these vectors defined? T is a unit tangent vector. So if my vector valued function defining the curve is, say, R of S, where S is arc length, then the formula for T is simply dr ds. How about N? N is also a unit vector, so length 1. It points in the direction of change of T. So as T rotates, N points in the direction of that rotation. And that's going to change depending on where the point P is on the curve. N points in the direction of the rotation of T. Curvature is how much T changes with respect to arc length. So curvature, denoted by kappa, equals the absolute value of dt ds. Then the vector dt ds, scaled to unit length by dividing by kappa, produces the principal unit normal vector, n.
Okay, so boleh faham tak? Dia dah terangkan tangent, normal, lagi satu curvature pun dah diterangkan juga dalam video ni. Then saya akan tunjukkan how to calculate. Macam mana kita nak calculate tangent vector ni and normal vector. Di sini mana dia example agak simple sikit.
Today we're going to be talking about how to find the unit tangent vector and the unit normal vector of a vector function. And in this particular problem, we've been given the vector function r of t is equal to, and here we've just been given the vector components t, 3 cosine t, and 3 sine t. Now, of course, sometimes you'll see this written instead as r of t is equal to ti plus 3 cosine t j plus 3 sine t of k, and of course those are equal to one another. It's the same thing. So whether you've just been given the components like this or you've been given the full vector function, either way we're just looking at those coefficients. Now, as a reminder, we have the formulas here for the unit tangent vector, which is going to be denoted by this capital T of t here. And as you can see, the unit tangent vector we find by taking the derivative of r of t, so we get r prime of t. And then we also are going to need the magnitude of r prime of t, which we'll talk about in a second. And then we have the equation for the unit normal vector, which we denote with this capital N of t. And it's really important to realize, of course, that the unit normal vector we're going to find with the unit tangent vector. So notice we have the derivative of the unit tangent vector and the magnitude of the derivative of the unit tangent vector. So obviously we're going to need to find the unit tangent vector before we can find the unit normal vector, since we use the unit tangent vector in the formula for the unit normal vector. So let's go ahead and start with the unit tangent vector. We can see that the first thing we're going to need is the derivative of r of t, which is r prime of t. So we can do it one of two ways. We can use this full vector function here and take the derivatives, or we can just use the components. Either way, we're just taking the derivative of each of these components individually. So let's go ahead and say that r prime of t is going to be equal to, we'll use the components since that's what we were given. So the derivative of t is 1. The derivative of 3 cosine t is negative 3 sine of t, because the derivative of cosine of t is negative sine of t. So we just pull that negative sign out in front of the 3, and the 3, of course, is going to stay. Then the derivative of 3 sine of t is 3 cosine of t, like that. So now here we have the derivative r prime of t. We're going to need that for our numerator. We're also going to need the magnitude of r prime of t. And the way that we find that, we denote it like this. The way that we find that is by taking the square root of the sum of the squares of each of these components. So all we're going to do is take each of these components, square it, add them all together, and put them under the square root sign. So squaring 1 here, we're going to get 1. Then we're going to add to that the square of negative 3 sine of t. Well, when we square that, the negative 3 times negative 3 becomes a positive 9. And sine of t times sine of t, we get sine squared of t. Then we're going to add to that the square of 3 cosine of t, which is going to be 9 cosine squared t. And all that's going to go under our square root sign. Now all we have to do is simplify this. So the first thing we're going to do is factor a 9 out of this sine squared t cosine squared t. So we'll get 1 plus 9 times the quantity, sine squared t plus cosine squared t. And the reason we do that, hopefully you've realized by now, is because we know from the trigonometric identity that sine squared t plus cosine squared t is equal to 1. So we can substitute for this whole value just a value of 1. 9 times 1 gives us 9. So then we just have the square root of 1 plus 9, or the square root of 10. Now, when we're talking about finding the unit tangent vector, we have the two components we need. We have the derivative of r of t, r prime of t, and we have the magnitude here of the derivative. So we're going to take this value here, r prime of t, these components, plug them into the numerator, and then take this square root of 10 and plug it into the denominator. So really, we just have this value right here divided by, if we just put a big division line, divided by this value right here in the denominator. But instead of writing it that way, we're just going to pull this square root of 10 out in front, and we're going to say that the unit tangent vector, capital T of t, is going to be 1 over square root 10, we pull that out in front, multiplied by these components, 1 negative 3 sine of t, comma 3 cosine of t, like that. And that's how we'll define the unit tangent vector. When it comes to finding the unit normal vector, we're going to follow a very similar process, because remember, with our original vector function, we had r of t, we found its derivative, and then the magnitude of the derivative. Well, now we have this unit tangent vector, capital T of t. We need to find its derivative and then the magnitude of its derivative. So we're just going to be starting with this vector instead of starting with this vector. So the first thing we need to do is find the derivative. So we'll say capital T prime of t is going to be equal to the 1 over square root 10 is going to stay out in front here. Now we just need to take the derivative of each of these components. So the derivative of 1 is 0. The derivative of negative 3 sine t, well, we know the derivative of sine of t is cosine of t. So the negative 3 is going to stay, and we're just left with negative 3 cosine t. Now here, the derivative of cosine t is negative sine of t, so we end up with negative 3 sine of t, and that is the derivative of our unit tangent vector, capital T prime of t. Now before we find the magnitude of this vector, we want to go ahead and factor out a negative 3 in order to simplify this as much as we can. Notice that we have a negative 3 in front of both the cosine t and sine t here, and if we factor out a negative 3 from the 0, we still just end up with 0. So we can say negative 3 over root 10 multiplied by the components 0 cosine of t and sine of t. So that'll make it a little bit simpler to plug into our unit normal vector formula. Now we need to go ahead and find the magnitude. So we're going to say the magnitude of capital T prime of t is going to be equal to, again here we're going to do the square root. Now it's important that because this negative 3 over root 10 is multiplied by each of these components, we need to include it in our square root sign here. So we're going to square that as well, because remember, we're going to square each of these components and take the sum. So we'll say negative 3 over root 10 squared. And then we're going to multiply this by the sum of the squares of each of these. So 0 squared is just 0. I won't write that. Cosine of t squared is just cosine squared of t. And then sine of t squared is just sine squared of t, like this. I'm going to put it all under the square root sign. Of course, here I have cosine squared t plus sine squared of t, which is just 1. So since this is multiplied by 1, that can just drop away. Now, when we square what we have left here, we're going to put that under the square root sign. We're going to get positive 9 in the numerator. In the denominator, we're going to get square root of 10 times square root of 10, or just 10. But of course, we still have to take the square root. So what we're going to be left with is just 3 over root 10. Now, to find our unit normal vector, remember that we have here the derivative of our unit tangent vector divided by the magnitude of the derivative of the unit tangent vector. We found those two components. Basically, we're saying this value here divided by this value here that we just found. So as you can see, we have this negative 3 over root 10 in the numerator. We have this 3 over root 10 in the denominator. Those will cancel, and we'll just be left with this negative sign here, the negative 1. So now, instead of leaving this negative sign out in front, we can go ahead and distribute it across our components here. And we can say that the unit normal vector, we'll write it up here, n of t, is going to be equal to, and we can just write the components like we just wrote the components for the unit tangent vector. We'll say 0, negative cosine t, negative sine of t. And of course, we distributed that negative sign to the 0, but we can't write negative 0, so we just leave that 0, and we distribute the negative signs there. So we end up with an equation here for the unit normal vector, and an equation here for the unit tangent vector. So that's how you find those two vectors for a vector function r of t.
Okey. Itu je Yang penting awak ingat formula. Kalau unit tangent vector, derivative R tu, maksudnya kita derivation R bagi dengan magnitude derivative R. Okey. Normal vector sama, cuma dia guna derivative tangent. Okey, biasa kalau soalan keluar pun dia akan minta cari tangent dulu, unit tangent vector, then yang kedua akan cari unit normal vector. Okey, seterusnya video ni akan terangkan tentang binomial vector. Okey, dapat teka mana satu binomial? Yang warna putih tu lah kan, binomial. So dia sebenarnya 90 degree kepada unit tangent dan dia 90 degree pada unit normal. Okey. So dia tu lah. Kalau tanya unit normal mana yang warna hijau tu? Dia selari dengan garisan biru ni lah. Dan dia setentang dengan dia tu yang warna merah tu ialah unit normal lah. Okey. Terbalik pula saya cakap. Yang warna hijau tu unit normal, warna merah tu unit tangent. Okey, sorry. Okey, dan macam mana pula kita nak kira binomial vector ni pula? Guna formula je.
Welcome to a lesson on the binomial vector. The goal of the video is to determine the binomial vector to a curve defined by a vector-valued function. Looking at this purple space curve here, this red vector would be the unit tangent vector. This blue vector here would be the unit normal vector. And this black vector here is the new vector, the binomial vector. And the binomial vector is orthogonal or perpendicular to both the unit tangent and the unit normal vector. And since it's orthogonal to both of these vectors, it makes sense that in order to determine the binomial vector valued function, we must determine the unit tangent vector valued function cross with the unit normal vector valued function. Let's go and take a look at this in space to get a better feel for this. Again, here we have the space curve in purple, the unit tangent vector in red, unit normal vector in blue, and the binomial vector in black. Remember that the red tangent vector points in the direction of motion, and the unit normal vector points in the direction in which the curve turns as t increases. So as t increases, you can see how these three vectors are oriented, but at all times they are orthogonal to each other. You could almost think of this almost as a roller coaster, where the red vector tells the direction of the roller coaster, the blue vector tells in which direction the roller coaster is turning, and the black vector, the binormal vector, would be you on the roller coaster ride. Okay, so let's go ahead and see if we can determine a binormal vector. Here we want to determine the binormal vector at t equals pi over 2 to the given vector valued function. So we know we have to cross t of t and n of t, so we first have to determine these two vector valued functions. So let's go ahead and do that. So here's how we'll determine r of t. We'll find the derivative of this vector valued function. So we're going to have negative sine t, cosine t, and 1. And then we'll divide this by the magnitude. So if we square this, we'll have sine squared t plus cosine squared t plus 1. Well, sine squared t plus cosine squared t is going to give us 1. So it looks like we'll have the square root of 2 here. So our unit tangent vector valued function will be negative sine t over square root of 2 for the x component, cosine t over the square root of 2 for the y component, and 1 over the square root of 2 for the z component. Now let's go ahead and see if we can determine the unit normal vector valued function. So we have to find the derivative of this and then divide by the magnitude. So we're going to have negative cosine t divided by square root of 2. Then we're going to have negative sine t divided by the square root of 2. And then the z component is going to be 0. You divide this by the magnitude, so we're going to have the square root of, this will be cosine squared t over 2, plus, when we square this, we're going to have the sine squared t over 2. This should be 0. Let's take a look at this radical a little more closely. We already have a common denominator, so we're going to have cosine squared t plus sine squared t all over 2. That's going to give us 1 over 2, or 1/2. This is going to end up being the square root of 1/2, which is the same as 1 over the square root of 2. Let's go and simplify this one more time. This is going to simplify nicely. Now, instead of dividing by 1 over the square root of 2, remember we can multiply by the reciprocal, so we can change this to times square root of 2 over 1. And we can see that these square roots are going to simplify nicely. So our unit normal vector valued function is going to be just negative cosine t for the x component, negative sine t for the y component, and 0 for the z component. So now to find the binormal vector valued function, we're going to have to cross this vector and this vector. And then we'll evaluate that at t equals pi over 2. Let's go ahead and do that on the next slide. So go ahead and determine this by evaluating a 3×3 determinant. So the first row is ijk, the second row is from the components of the first vector, and the third row are the components from the second vector. Now we'll evaluate this 3×3 determinant by using the cofactor expansion method. So here we're going to eliminate row 1 and column 1. Here we'll eliminate row 1, column 2. And then lastly, we'll eliminate row 1, column 3. Let's go and evaluate these. Here we're going to have 0 minus negative sine t divided by the square root of 2. It's going to be positive sine t over the square root of 2. Here we're going to have 0 minus negative cosine t over square root of 2, which will be plus, but then we are subtracting, so it's still going to be negative cosine t divided by the square root of 2. Here we'll have sine squared t over square root of 2 minus a negative cosine squared t divided by the square root of 2. The numerator is going to be sine squared t plus cosine squared t. That's going to be 1. Our denominator will be the square root of 2. Let's go ahead and take this onto the next screen and evaluate this at pi over 2. Well, the sine of pi over 2 is going to be 1, so the x component will be 1 over the square root of 2. But cosine of pi over 2 is 0, so the y component will be 0. And then lastly, the z component will be 1 over the square root of 2. This would be our unit binormal vector. Let's go and take a look at this. Here's our space curve in purple. Again, our unit tangent is in red, unit normal is in blue, and our unit binormal is in black. So when t is equal to pi over 2, which is approximately 1.57, the unit binormal vector that we found was something very close to this black vector here that we see. And again, notice all three of those are orthogonal to each other. Okay, that's going to do it for this video. I hope you found it helpful.
Okey, terima kasih menerangkan ya. Itulah cara nak kira binomial. Just times lah. Tangent times a normal. Okey. Okey, this last one. Macam mana kita nak calculate curvature. Tapi sebelum ni, video ni akan tunjuk dululah apa itu curvature.
Hello everyone. So what I'd like to do here is talk about curvature. Curvature. And I've drawn on the xy plane here a certain curve. So this is our x-axis, this is our y-axis. This is a curve running through space. And I'd like you to imagine that this is a road of some kind, and you're driving on it, and you're at a certain point. So let's say this point right here. And if you imagine what it feels like to drive along this road, and where you need to have your steering wheel, you're turning it a little bit to the right, not a lot, because it's kind of a gentle curve at this point. You're not curving a lot, but the steering wheel isn't straight. You are still turning on the road. And now, imagine that your steering wheel's stuck, that it's not going to move, and however you're turning it, you're stuck in that situation. What's going to happen, hopefully you're on an open field or something, because your car's going to trace out some kind of circle, right? Your steering wheel can't do anything different. You're just turning it a certain rate, and that's going to have you tracing out some giant circle. And this depends on where you are, right? If you had been at a different point on the curve, where the curve was rotating a lot, let's say you were back a little bit towards the start. At the start here, you have to turn the steering wheel to the right, but you're turning it much more sharply to stay on this part of the curve than you were to be on this relatively straight part. And the circle that you draw as a result is much smaller. And this turns out to be a pretty nice way to think about a measure for just how much the curve actually curves. And one way you could do this is you can think, okay, what is the radius of that circle? The circle that you would trace out if your steering wheel locked at any given point. And if you kind of follow the point along different parts of the curve and see, oh, what's the different circle that my car would trace out if it was stuck at that point, you get circles of varying different radii, right? And this radius actually has a very special name. I'll call this R. This is called the radius of curvature. And you can kind of see how this is a good way to describe how much you're turning. Radius of curvature. You may have heard with the car descriptions of the turning radius. If you have a car with a very good turning radius, it's very small, because what that means is if you turned it all the way, you could trace out just a very small circle. But a car with a bad turning radius, you don't turn very much at all, so you'd have to trace out a much larger circle. And curvature itself isn't this R, it's not the radius of curvature, but what it is it's the reciprocal of that. 1 over R. And there's a special symbol for it. It's kind of a K, and I'm not sure in handwriting how I'm going to distinguish it from an actual K. Maybe give it a little curly there. It's the Greek letter kappa, and this is curvature. And I want you to think for a second why we would take 1 over r. R is a perfectly fine description of how much the road curves. But why is it that you would think 1 divided by r instead of r itself? And the reason basically is you want curvature to be a measure of how much it curves in the sense that more sharp turns should give you a higher number. So if you're at a point where you're turning the steering wheel a lot, you want that to result in a much higher number. But radius of curvature will be really small when you're turning it a lot. But if you're at a point that's basically like a straight road, there's some slight curve to it, but it's basically a straight road, you want the curvature to be a very small number. But in this case, the radius of curvature is very large. So it's pretty helpful to just have 1 divided by r as the measure of how much the road is turning. And in the next video, I'm going to go ahead and start describing a little bit more mathematically how we capture this value. Because as a loose description, if you're just kind of drawing pictures, it's perfectly fine to say, oh yeah, you imagine a circle that's kind of closely hugging the curve. It's what your steering wheel would do if you were locked. But in math, we will describe this curve parametrically. It'll be the output of a certain vector valued function. And I want to know how you can capture this idea, this 1 over r curvature idea, in a certain formula. And that's what the next few videos are going to cover.
Okay, faham curvature tu? Dari segi bulatan je lah. Perbezaan dari segi radius tu. This one calculation lah. Macam mana kita nak determine the curvature.
Find the curvature and radius of curvature of the vector function at t equals 5 pi over 6. The graph of r of t is shown below in blue. The graph is an ellipse in the xy plane. Let's review curvature and radius of curvature. The curvature at a point measures how sharply the curve bends or how quickly it changes direction. The curvature of a line is 0. The curvature of a circle is equal to the reciprocal of the radius. More formally, the curvature measures how quickly the direction of the unit tangent vector changes with respect to a change in arc length s. When we have a space curve in 3 dimensions, we normally use this formula here to determine the curvature. In our case, because we have a plane curve, we'll be using a simplified formula, which we'll talk about in just a moment. Let's first look at an animation. Here we have a function graphed in black. In blue, we will see the circle of curvature as we animate a point along the curve. If we stop here for a moment, remember the radius of the circle of curvature and the curvature of the function are reciprocals of one another. So right here, the circle is fairly large, which means the radius is fairly large, resulting in a small curvature. But as we approach this bend in the curve, the circle of curvature gets smaller and the curvature of the function gets larger. So right here, the radius of the circle of curvature is small, resulting in a much larger curvature. Let's animate this point in the circle of curvature along the curve. Again, the curvature is equal to the reciprocal of the radius of the blue circle, which is the circle of curvature. Going back to our example, because we have a 2-dimensional vector function, the z-component is equal to 0. So if we apply this formula for the curvature with a z-component of 0, the curvature formula simplifies to the formula we see here. So for this example, we'll be using the simplified formula for the curvature, which again only applies when we have a plane curve, not when we have a space curve. So for the given vector function, x of t is equal to 7 cosine t, and y of t is equal to 3 sine t. Now we need to find the first and second derivatives of x of t and y of t. So x prime of t is equal to negative 7 sine t. X double prime of t is equal to negative 7 cosine t. And y prime of t is equal to 3 cosine t. And y double prime of t is equal to negative 3 sine t. And now we can determine the curvature as a function of t. The curvature k is equal to, in the numerator we have the absolute value of x prime of t times y double prime of t, which is negative 7 sine t times negative 3 sine t, minus x double prime of t times y prime of t, which is negative 7 cosine t times 3 cosine t. So we have the absolute value of the difference of these two products. In the denominator we have the quantity x prime of t squared plus y prime of t squared raised to the 3/2 power, which gives us the square of negative 7 sine t plus the square of 3 cosine t, and all this is raised to the 3/2 power. And now let's begin simplifying. In the numerator we have 21 sine squared t minus negative 21 cosine squared t, which is equivalent to plus 21 cosine squared t. We have the absolute value of this sum. In the denominator, we have the quantity 49 sine squared t plus 9 cosine squared t. And this is all raised to the 3/2 power. Let's continue on the next slide. Looking at the numerator, we have a common factor of 21. To factor out the 21, we have 21 times the quantity sine squared t plus cosine squared t. We should recognize that sine squared t plus cosine squared t is equal to 1, and therefore the numerator simplifies to the absolute value of 21, which is 21. And the denominator remains the same. We have 49 sine squared t plus 9 times cosine squared t raised to the 3/2 power. And now that we have the curvature as a function of t, we need to determine the value at t equals 5 pi over 6. So the curvature at t equals 5 pi over 6 is equal to 21 divided by the quantity 49 times sine squared 5 pi over 6 plus 9 times cosine squared 5 pi over 6. And all this is raised to the 3/2 power. And now we need to find sine 5 pi over 6 and cosine 5 pi over 6, which we can find on the unit circle or using reference triangles. 5 pi over 6 would be this angle here in standard position, where the reference angle is pi over 6 radians or 30 degrees, and therefore we can label the opposite side 1, the hypotenuse 2, and the long leg square root 3. But because we're in the second quadrant, where x is negative, this would be negative square root 3. So using the reference angle theta, we can determine sine 5 pi over 6 and cosine 5 pi over 6. Sine is equal to the ratio of the opposite side to the hypotenuse, which is 1/2. Cosine is equal to the ratio of the adjacent side to the hypotenuse, which is negative square root 3 over 2. Which means the curvature at 5 pi over 6 is equal to 21 divided by the quantity 49 times 1/2 squared plus 9 times the square of negative square root 3 divided by 2, and all this is raised to the 3/2 power. Simplifying, we have 21 divided by the quantity 1/2 squared is 1/4, so we have 49 fourths, plus the square of negative square root 3 over 2 is 3/4. 9 times 3/4 is 27 fourths. All this is raised to the 3/2 power. And 49 fourths plus 27 fourths is equal to 76 fourths, which is equal to 19. So the denominator simplifies to 19 raised to the 3/2 power. So the curvature at 5 pi over 6 is equal to 21 divided by 19 raised to the 3/2 power, which is approximately equal to 0.25356. Now if we go back to our question, we're also asked to determine the radius of curvature, and remember, the curvature is equal to the reciprocal of the radius of the circle of curvature, which means the radius is equal to 1 over curvature. So the radius of curvature, which I'll call r, at 5 pi over 6 is equal to 1 over the curvature, or the reciprocal of the curvature, which is 19 to the 3 halves, divided by 21, which is approximately 3.94377. Now if we go back to the first graph for a moment, the circle of curvature for the ellipse at t equals 5 pi over 6 is shown here, and the radius of this circle, which again is a circle of curvature, is approximately 3.94, and the curvature of the ellipse at t equals 5 pi over 6 is approximately 0.25. I hope you found this helpful.
Okey, itu cara nak kira curvature. Basically sebenarnya chapter 3 ni bukan formula je, dan formula tu diberi dalam test of an exam. Cuma formula simple macam unit tangent vector tadi saya tak sure diberi ataupun tidak. Kalau simple sangat kadang tak diberi Okey. Okey, itu saja untuk video minggu ni. So saya rasa okey, ni dia individual worknya. Cuma awak abaikan sedikit yang submit online tu. Ni dulu untuk yang dulu saya buat kelas online lah, so tak online. Tapi awak akan buat secara individual dan awak kena submit pun individual. Okay, so dia soalan yang sama jugalah. Saya buat kalau ada masalah macam biasa boleh masuk saya, insyaAllah saya akan reply. Okay, yang awak masuk malam dan saya dah tidur pagi esok lah. Okay, itu saja. Terima kasih.